Okay, now we want to get back our original signal. So this is called reconstruction. So this term here, reconstruction. So we have a set of samples. Now I want to get this green signal back. That's my ideal world. But what can I really do? Well, I only have these samples. I don't know. Let's just say the signal looks kind of like nearby. So this would be piecewise constant, or sometimes called nearest neighbor, right? You just, for every continuous point, you say whatever was my closest sample, that's probably the value. We could do that. That's not very close to our original function in this case. We could try to do something better. We could do a linear approximation. So we were studying bilinear and linear approximations. Okay, here we go. Now we're going to draw a line between these things. Should be a better approximation, right? In this case, it's still way off. This function has too many wiggles in it. The technical term wiggles. No, it's not. You call this too high frequency in terms of what the signal is going on. But this can't approximate, right? This linear approximation doesn't get you close enough in terms of the reconstruction. So what can we do? Like, what are our choices? Well, we could add more samples. Adding more samples would be a way to try to get to this. So now I've got some things that happen on top of these wiggles. So now when I go try to reconstruct, either piecewise or linear, I get closer. I've recovered some of the shape of what's here. It's not perfect, but I've gotten better. So adding samples is something that helps in terms of later making the reconstruction more accurate. So let's see this on 2D pictures. Now I can't show you yet sort of what does this sampling look like in 2D in an easy way. So here we have some pictures. Unfortunately, they were scanned out of something and it was done on a black and white scanner, so it's not perfect. These were originally grayscale images. And we're going to consider one scan line going across this image. And the height of this is now going to be the intensity of the pixel. So up here is 255 white, and down here is 0 black, or you could say 1.0 if you want to say that. And I'm only showing one color channel. So for this kind of image, right, when I cross the line, okay, the intensity goes up and then it goes back down to black, right? And we can see that originally there was 2 different color objects here because we have 2 different intensities. If you take this natural picture of this mandrel, right, then the intensity plot across the image looks something like this. So we can treat our 2D pictures as just signals, where here I've drawn the plot of across a line, but you could treat this whole thing as a 2D signal. So what does our sampling and reconstruction look like? We have our original picture, which I'm going to draw a cross plot here of this thing. We sample, meaning we take a bunch of points, but in 2D, we're really taking a bunch of points all over the image. And then later, we're going to reconstruct this signal from just the samples. And we're going to hope that this signal equals what the original signal was, if we do things correctly. Okay, let's look at this from a triangle point of view. So here's a triangle. Here's our sampling, right? So sampling means we're going to take a bunch of points, and for each of those points, we're going to ask, is it inside our signal, or what's the intensity? And here our intensity is basically red or white. That's our choices, right? So you could say this is full power, this is no power, I guess, if you wanted to think of it that way. So the samples here are at discrete locations, just like we were talking about before, and there's only so many of them. There's a finite number, and they don't represent the whole signal properly because we sort of miss what's going on in between. Okay, so this is our sampled signal, right? We don't have the triangle anymore. We just have the samples left over. When we go to actually reconstruct this on our physical screen, if we're on an LCD, we've seen that our LCD treats these things as, well, not even perfect little squares because we have red, green, and blue inside, as we saw when we talked about this place. But let's suppose it basically makes a red square out of this, right? It definitely doesn't make the nice smooth edge. So we got some jaggies that came from the fact that we did sampling, and we're missing the information about exactly where does this edge go, right? So it's the same as we just saw in the 1D case that's going on here with this 2D triangle case. So here's our continuous function. Here's our sampled function, not the same thing. We wish we could fix this up.